Okay, so let's go ahead and look at this reaction from yesterday. We have zinc and zinc metal, and we have ferric oxide. Okay, so the zinc metal is in the solution of ferric oxide. Now, from now on till the end of the semester, whenever we have a salt, remember a salt is a cation plus an anion. And a common example is table salt. Notice I don't say salt, table salt. There are millions of salts out there. Sodium chloride happens to be the one we use in cooking. And most people refer to that as salt, but it's one of millions of combinations. Whenever I say salt, you automatically think of two ions, positive and negative. The other thing you need to do from now on is to distinguish that by doing AQ. AQ stands for aqueous. That means that salt is dissolved in water. Now, when you take an organic chemistry class, it may not be dissolved in water, it may be dissolved in a solvent like pentane or hexane or something like that. But as far as our class is concerned, and the next chemistry class you take, it's going to be dissolved in water. Okay, so aqueous. Now, part of the write-up for this lab, they're going to ask you to label it. The other thing they want you to label is the zinc. And what is zinc? Is it gas, liquid, or solid? Solid. So you're going to have these subscripts. Now, when we get into double replacement reaction, it's going to be the same thing. Aqueous, solid, liquid, or gas. Okay, so let's go and do this problem again. So the question is this reaction going to go? Now, I want to tell you, this is probably the most complicated stuff we've done so far. We're bringing together balanced equations, we're looking at some other things, and it's getting involved. And the more you get into chemistry, the more involved it gets. You just start bringing in all this other stuff and bringing it together. Unit 4 particularly, and Unit 5 is going to be like that. Okay, so let's look at zinc and iron here. Okay, so the salt is below the metal. Salt is below the metal. That means a reaction happens. The reaction happens, the metal becomes an ion. And the cation becomes a metal. Now let's do the half reactions for each one of these to make sure we have our electrons balanced. So zinc. Oh, one other question that came up yesterday, that some of the people were doing the pre-lab and lab. I always put the metal first. You don't have to put the metal first, put it second. I just happened by habit since I took chemistry in high school, 1965. I've been doing it that way ever since. Put the metal first, but it doesn't have to be first. It can be second. Okay, the order does not matter at all. Okay, so the zinc is going to lose 2 electrons. It loses 2 electrons. and that's being oxidized. Remember, oxidation is you're losing and transferring electrons. What goes along with oxidation is reduction. Reduction captures electrons. And that means the iron +2 cation is going to capture those 2 electrons and going to become iron metal. Now, do we have to adjust these half reactions in terms of electrons? Are the electrons balanced? Yeah, 2 and 2. So nothing more to do. If we add these up, electrons cancel out, and the overall equation is going to be zinc metal plus iron +2 from the salt gives us now what's the spectator ion? Oxygen, right. Now we have to add the oxygen back in. Oxygen is a -2 from your common ion chart. It's going to be okay. So that's a very straightforward single displacement or single displacement reaction.
So what's the top?
What?
What makes CN aqueous? So it's solid on the left side, metal.
Aqueous means it's a salt, number 1, and number 2, it's dissolved in water. So just start labeling it from now to the end of the semester. Also, solid liquid gas, SLG, as well. Okay, so you need to know how to do this. There will be 2 problems on your test Tuesday, assuming we don't get a fire that starts like last year. They canceled school a number of days. It was just awful. Assuming we don't have any days where the power is off and we have to cancel class, it'll be on Tuesday. You'll have 2 of these single displacement and 2 double replacement, as well as some balancing equations and mole questions. And I'll give you a study guide as well. Okay, so any questions about this guy? Yeah. Zinc superscript 0 is a metal, zinc metal.
It's
Hmm?
0.
Yeah, 0 means it's uncharged or neutral, right? Now, a lot of times, depending on what textbook you have, what instructor you have for your next class, it may or may not put the 0 there. I do. I like to make sure everyone knows that's a metal. So does that make sense? Okay. All right. Are we okay with? All right. So let's now go on to double replacement reactions. Now, sometimes you'll see it as displacement, other times replacement. Now, your lab talks about displacement. And it depends, again, what textbook you're reading. It could be either displacement or replacement. Now, yesterday, was it yesterday or day before yesterday? I passed out the handout, and I have extras. So make sure you pick up one of these if you didn't get it last time. Okay, we're going to be working with something called solubility rules. These are the solubility rules. They call it a guideline. In your next class, you may or may not have to memorize those rules. But what I did is I put together the solubility table, so it's in graphic form and very visual. So what this does, this tells you if you have a cation and an anion together in solution, aqueous, whether it'll form a solid or not, or it'll stay apart. Now, I want you to remember there are two forces at work when something becomes a solid. There is the solvating force and the crystal lattice force. And those are competing forces. If the crystal lattice force is stronger, you get a solid. If the solvating force is greater, you have no change. In other words, the ions stay apart. They don't form a crystal. All right, so that's what's driving these rules, are these two forces. So whenever you talk about solubility stuff, you have to specify a temperature, because when you warm things up, the solvating force becomes stronger. When you cool it down, it becomes weaker. The crystal lattice force does not change with temperature. Just like when you have a cup of coffee, iced coffee, the sugar doesn't dissolve, you heat it up nice and hot, it dissolves right away. So the solvating force will increase with increasing temperature. Okay, so how do you use this table? Well, you can use the rules if you like, or you can use this table. Basically, we have the anions here, cations up here. And where they come together is either going to be white or black. Black means a solid forms, white means it stays in solution. So let's say is that silver chloride solution going to be aqueous or S? Which is it going to be? So what you do using this chart, you're going to find chloride right here. And here's silver. That's where they come together. So because it's black, they form a white solid. Now the solids can be other colors as well, not just white. I would say the predominant color is pretty much white. White means it disperses light evenly instead of reflecting it back. When you see something is red, like this, that means that the red is being reflected back. Everything else gets absorbed. The black, that means everything is absorbed. White, nothing is absorbed. Everything's reflected back. So when you dye clothes, the dye is made up of certain chemicals that absorb light in a certain way. That's why the dyes are different colors. In fact, there's a class over at Sac City called Chemistry and Art. And no one's qualified to teach it anymore, but it was a really cool class where they actually went in and looked at things like frescoes and oils and chalk and stuff, and also in ceramics, why glazes are certain colors. Really kind of a cool class. I would have liked to have taken the class personally. Okay, so let's talk about double replacement reactions now. So that's how to use the solubility table as you're doing this bit. Now, when you get into the double replacement lab, you're going to predict whether you're going to get a precipitate or not. Oh, the other thing is, okay, when it forms a solid, a fancy word for that is called precipitate, or PPT for short. You can use either one. Depends on your book, depends on the lab. So those are be used interchangeably. Okay. Okay. Single replacement is metal plus salt. Double replacement is salt plus salt. Oops. All right, so let's look at this now. Remember, salts are now aqueous. They're dissolved in water. So let's take table salt, and let's take silver nitrate. And we are going to dump them together. So what that's going to look like is we have a beaker. Sodium chloride dissolved in water. And because it's dissolved in water, the ions come out. And it's really sodium ion, chloride ion, separate, because I said aqueous. And over here, we have a solution of silver nitrate, aqueous. So what we're going to do is we're going to take this guy and dump it in there. That means the sodium now has a choice who to hook up, who to hook up with. The sodium can either hook up with a chlorine or the nitrate. So we have two new combinations. We have the originals. We have two new combinations. So the question is, do the new combinations form a solid or not? That's where your tables come in. So that's the one I just showed you. So we've got the new, one of the new combinations is chloride and silver that ends up being black. That means that's a precipitate or a solid. The other one was sodium nitrate. That's white. That means they don't form a solid. Okay, you see how you can use that table now?
Blacks are solids, whites are solids.
Yeah, blacks are solids, white is just still in solution. Yeah. In other words, nothing appears to happen. No visible reaction. All right, so That means that silver chloride is going to be solid. The sodium nitrate is going to remain aqueous. White square, aqueous, black square, solid. Now it could be solid, liquid, or gas too, by the way, but most of the time it's going to be a solid. Okay, so how would we write that in the equation? So the way we're going to do that is we're going to bring the silver and the chloride together as a solid. Plus the sodium nitrate as aqueous. So what we just wrote was called a molecular equation. Now there are three equations from this reaction. Now the reason why it's molecular is because the aqueous stuff are together, when in reality they aren't together. So this is what it looks like if we take them apart. Okay, so I took all the aqueous stuff apart into individual ions, except the solid, because that's together. That's together. Okay, and this is called the total ionic equation. And it's an equation, so we have to make sure it's balanced, of course. And this is balanced because everything is singles. And there's one more equation. That equation is called the net ionic equation. What does the word net mean? Someone says net it out. What does that mean? Who's heard of that before? Anyone? Okay. And what is it? What did you, when you heard it, what did it mean to you? And it took out the stuff that didn't matter, right? Okay. That's the key. What's the stuff that doesn't matter in this equation? Spectator ions. They don't do anything. So what are the spectator ions in the total ionic equation here? Two of them. It's always two, yeah. What was the first one? That's one of them. What's the other one? Nitrate's the anion. What's the cation? That's spectator ion. Sodium. Two spectator ions. Okay, so eliminating the spectator ions, we have so that's the net ionic equation. Now, sometimes nothing happens. You dump two solutions together, nothing happens. That means you do not have a net ionic equation. Something's got to happen before you get the net. Now, we need to list the spectator ions. Those would be the spectator ions. Okay. Now, I think this is easier than the single replacement, but there's a lot of little parts that you can forget to put in. And that's what kills students are the little parts. They understand the concept well. Mix two together, you get a solid, boom. Everything else is aqueous, dissolved in solution. High solvating force at work. It's all the details. All in the details. Okay, are there any questions about the process?
The entire second part of the salt is spectator. I mean, yeah, the entire second part. So you did A2Cl3 plus NaNO3, and the NO3, that entire part, NaNO3 is the spectator.
Yeah, exactly, exactly. And that's because when you bring these two together, it's a white box. So white boxes are spectator ions. Black boxes are in the net. Now that is a very straightforward double replacement reaction. It's not multivalent. And they're not plus twos and plus threes involved. It's just plus ones all the way across. And when you get to your next class, they're going to be mixing this up a lot. So in here, I want you to know the basics extremely well. So when they hit the basics in your next class, it's total review for you. And I know some of you are transferring directly next semester to a four-year school. And frequently the four-year schools do not have prep classes like this. They just throw you into 1A, have a nice day. That's why they have 40 to 50% dropout rate in those classes. Okay, does this concept make sense? Is it okay? We just need lots of practice. So one, your lab is going to give you lots of practice, and so for unit 3, Canvas files, here's net ionic equations. That would be double replacement reactions. If you want more practice. Unit 3, yeah. I think I'm in unit 3, aren't I? So notice these are aqueous and aqueous. And of course, here are the answers. Did you find it?
Yeah.
Okay. And then, okay, it doesn't look like there's a single replacement activity sheet in there. I'll have to put one in. Are you guys finding the practice sheets of value? So definitely include them then. Right? Okay. With answers, right?
Is that how you do it?
Sometimes they're different files. Depends on where a lot of these are really old. And it's just over the years been collecting them. All right, so let's do some more. Okay, let's do another practice problem here. Um, okay, so we're going to take potassium chloride aqueous, sodium carbonate aqueous. Let's not do carbonate. Let's carbonate. Yeah, I wanted to do another one. Carbonate is -2. No, that's -2 also. Let's do like that. Okay. All right, so we have potassium chloride plus sodium sulfide, both aqueous. Dump those together. What is the new combination? The new combination is going to be KS plus sodium chloride.
Gas aqueous then too.
Well, we don't know. We have to look on the solubility table. So KS, find the K. It's white. That means this is aqueous then. Can't read it very well. Let me read. Okay. And what about the sodium chloride? Also white. Now, is this balanced? No, it's not. So always make sure your equations are balanced. No exceptions. Okay. So if we put 2 potassiums on the right, 2 potassiums on the left, 2 sodiums on the left, 2 on the right. Okay, so we got 2 sodiums, 2 chlorides, 2 chlorides, 2 sodiums, 1 sulfur, 1 sulfur, 2 chlorides, 2 chlorides. So it's balanced now. All right, so that's the molecular equation. Sometimes they abbreviate that as an ME. Guess what TIE stands for? Total ionic equation. Okay, so that means we're going to split up everything. Now notice it's all aqueous on both sides. Okay, when you look up on your solubility table, all those combos, the new combinations are white. So is there a net ionic equation? No. So if I ask you to write the net ionic equation, it's going to be null set. Okay, or you can write no net ionic equation. Either way is fun. Okay, so let's write the total ionic equation. So we're going to split everything up. Now we have a lot of parts because everything's aqueous. So how many Ks do we have? Two. How many chlorides? Two. Okay, so we have two Ks, two Cls. Two sodiums. One sulfide.
I mean, that was cute.
Oh. Yeah, should be A2. Okay, so that's on the reactant side. See, what have we left off here? Chlorine, okay. Okay, so that's the total. So no solid formed, no precipitate form, no liquid or gas form. So we have no net ionic equation. What are the spectator ions? Everything's spectator. If no precipitate happens, everything is spectator. So that means it's going to be K, Cl, sodium, and sulfide. Those are the spectator ions. So if nothing happens, everything is spectator. That means the solvating force is very strong. It overcame the crystal lattice force. Okay.
change next to solving force?
Hmm?
Why in the notes was no change written next to solving force?
Well, the solvating force keeps the ions apart.
Yeah,
Crystal lattice keeps them together.
Okay.
So if they're all apart, that means the solvating force is dominant.
and so they stay all apart, but we're not changing.
Exactly. And then in the case of the solid forming, then the crystal lattice force is stronger. Kind of like Star Wars, right? These competing forces. Okay. All right. So this just takes practice. And that one worksheet on your Canvas will give you a fair amount of practice, as well as your lab. Okay. Now something in this, are there any questions about this? Okay.
So, on the solubility table, blacks are solids, and then whites are aqueous plus gas.
Yep, exactly. And you're going to get that solubility table on Tuesday in the part of the test. Okay, so we've talked about single replacement, double replacement reactions, equation balancing, moles, Avogadro's number, and gases. Now there's two more topics for unit 3 I want to cover. One is temperature. We haven't talked about temperature. We haven't talked about gases. So today I want to finish up here talking about temperature. And then tomorrow I want to talk about gases. Okay, who's heard of temperature? Gosh, everyone's raising their hand, right? What is it? What? Measure of heat. That's good. What's heat? Yeah. Yeah. And to be more specific, kinetic energy. And kinetic energy is the energy of motion. Okay, so the metric we're going to be using, there are two metrics. Actually, there are four. I'm going to talk about two. Centigrade and Fahrenheit. And they're both a metric. One's an old metric, the Fahrenheit. When I say old, older than 200 years. The other one is more current, and that's centigrade or Celsius, C. The world uses C except for 7 countries. We're the only superpower that uses the imperial system. That's pounds, ounces, quarts, gallons, etc., and Fahrenheit. So Fahrenheit is not an SE unit. It's not a standard metric unit at all. Celsius is. So normally in science classes, like 99% of the time, we're going to be using C in here. So centigrade, centi means 100. Keep that in mind. So that's IU. That's supposed to be a U here. So no, that's not right. Celsius, yeah. Isn't that spelled right now? Okay. Normally, my mind as I'm writing, I'm doing phonetics. I left that out. Okay. So in the Celsius system, Water boils at 100 degrees. Boom. At 1 atmosphere. One atmosphere pressure. Water freezes at 0 degrees Celsius. So what's the difference between temperature-wise 0 and 100? Delta what? 100. And that's where the centigrade comes in, or Celsius. A lot of people use centigrade because there's 100 degrees separating freezing water and boiling water. So everything is nice and metric. Now to contrast that, we have Fahrenheit. Water boils at 212. Now, to go from one to the other, there's a formula you can use. It's called well, Atua. We're always going to use Celsius in here. We're not going to use Fahrenheit. I taught an introductory class up in Tacoma, and part of it was chemistry and cooking. And so we use Fahrenheit there because it was cooking. But normally in science classes, it's Celsius only. Bless you. Okay, so okay, so temperature is a metric for measuring the kinetic energy of an atom or molecule. It's not heat. It's a measurement of movement. And heat is manifested as motion. That's why you always associate temperature with how hot something is or how cold something is. Okay, now, so everything around us is moving. This thing is moving. My hand is moving. This computer, if it has an atom or molecule in it, it's moving. When you get into 1A, you're going to calculate the speed at which stuff moves quite a bit. So what happens when it doesn't move? Okay, if temperature is a measurement of movement, then if movement is 0, that means all movement is stopped. So what we're going to do is we're going to cool it down, cool it down, cool it down, cool it down until the movement slows down to almost nothing, then stops. That's called absolute temperature. 0 degrees. However, not Celsius though. That's at minus 273 degrees Celsius is when movement stops. Um, 4 something, I believe. I mean, I never used Fahrenheit in chemistry, but I think it's 4 something.
Why don't they just write it at 0? Why is it-
Because Celsius is just arbitrary points that someone chose. Up, water frozen, let's just choose 0. Water boils, let's choose 100. And then we divide up 100 points in between those two. So it's arbitrary,
So freezing, movement, stopping, different.
depending on the atom or molecule. That's why they had to say water. Okay, so again, Celsius and Fahrenheit are both relative. We have an absolute temperature scale also. That's not relative. It's defined by absolute, no movement at all. So that's Kelvin. So oops. So at 273 Kelvin is when water freezes. No, it's positive. Kelvin is all positives, no negative. Because when you go negative, you're going below the freezing point of water. Well, you can't get below absolute 0. The movement has already stopped, so you can't go negative movement. If you could. Okay, so all thermodynamics is done in Kelvin. Okay, engineers work frequently with Fahrenheit. And that's called Rankine. And that's for absolute 0. It's going to be 0 Rankine. And we're not going to be using any of those imperial stuff in here, all metric system. So you need to be able to convert okay, so how do we convert to Kelvin? We take C plus 273. Oh, from Kelvin to centigrade, Kelvin to Celsius. It's a very simple relationship. And the units of Celsius and Kelvin are the same units. So a degree Kelvin is equal to a degree Celsius. I'm sorry? 270 where? Oh, it's 270. Just 273. It depends on your instruction for your next class. They may say 273.3, but I just do 273. Now, tomorrow we're going to be working with gases. The relationship for gases is a Kelvin relationship. So whenever we do conversions like pressure, volume, temperature, the temperature part is going to be in K. So if the problem states it in Celsius, you need to convert to K. Okay. I can, and we're not going to do conversion. Okay. The only conversion we're going to do is between Kelvin and Celsius, which is pretty straightforward. The other one is like 9/5 plus 32 and all this stuff. And you never convert back and forth anyway. So we're in a science class. So All right, that's what I wanted to cover today. So temperature is very straightforward. Temperature is the metric we use as to how much kinetic energy an atom or molecule or particle actually has. Say again? Yeah, I like to put that in so everyone knows it's degrees. Because they're going, K, is that potassium? I mean, it also will depend on your next chemistry class too. Are you going to take a chemistry class here? Are you signed up for one for the fall? Oh, the wait list.
Yeah.
Yeah. It's ridiculous. Chemistry classes fill up like it's ridiculous. And we have 17 sections of 2A, and they're all full. And they're needing 3 instructors. We're short 3 people. Yeah. And Sac City's the same way. Their 2A class is called 305, and it's the same thing. 17, 18 sections. It's crazy.
I don't think it's
The lab. It has to be a hands-on lab. Lectures are easy. You just do it online. Problem is the labs.
yeah, you just divide the labs up. And then spend the time with teachers with the teaching and do that.
That's why they love the fact that I teach Friday, Saturday here in the fall and spring. Because I don't take up lab space during Monday through Thursday. And in fact, they've moved 2A classes over to Friday, Saturday as well.
So you're saying that the lab space is already capped.
Both schools.
Right.
And every school I taught up in Washington State, labs were restrictive. And then by state law, you can't have more than 24 in a lab as well for fire safety reasons. That's why at the beginning of my classes, I overload because we're doing dry labs in the beginning. And so I can overload because we're not doing chemicals. But once we start doing wet chemistry, 24. So, all right, that's it for today. If you didn't pick up your test, I'll have them when I open up the lab.